Hello everyone and welcome to Infotainment Lounge. And today's video is about the reactions of alkenes. We started the reactions of alkenes in the previous live stream and it was not completed in that stream, so I'm going to continue from there. In fact, the last around 10 minutes of that stream were not clear because of some internet problems, so I'm going to start from the point till the content was clear. So students, if you are there, please say something in the comment section so that I may know that I'm live. Okay, so as I was telling you in the previous stream about the Markovnikov's rule, I will start right from this point because after that the video was not very clear and there were some cuts and repetitions in the video. So I will start from Markovnikov's rule. And it states that when an asymmetrical molecule is added to an asymmetrical alkene, the negative radical of the molecule tends to bond with the carbon atom with least number of hydrogen atoms. Now let us see what are symmetrical and asymmetrical molecules and what are symmetrical and asymmetrical alkenes. Okay, now let's see. See, this is a molecule of chlorine, Cl2. It has one single bond between two chlorine atoms, and if this bond is broken, the radicals produced from each side is the same. Like simple chlorine atom would be produced from this side, and a simple chlorine atom will be produced from the left side. So this molecule is a symmetrical molecule. Let us take another example, like if we are talking about hydrogen. Again, when we break this bond, one hydrogen. Let us take an example of asymmetrical molecules. For example, HCl, hydrogen chloride. In this case, again we have to break this bond, but when this bond is broken, two different radicals are produced. One side will produce hydrogen atoms and the other side will produce chlorine atoms. So this molecule is asymmetrical. Another example is H2O, water. See, whenever water is going to break down, it could break either this bond or this bond. It doesn't matter which bond it is breaking, the radicals produced would be different. one side would produce OH group and the other side would produce hydrogen group. That means this molecule is asymmetrical. Now let us see which alkenes are symmetrical and which ones are asymmetrical. Like if we talk about ethene, now you have to check from the position of the double bond. If you break the double bond, then in this case each side will produce same radicals. Like on the right side there is a CH2 group and on the left side there is a CH2 group as well. That means this is a symmetrical alkene. Another example, see, this is butene. Now if you break this double bond between carbon atoms, again same radicals would be produced from each side. This side has 2 carbon atoms and 4 hydrogen atoms, and this side too has 2 carbon atoms and 4 hydrogen atoms. So this alkene, butene, is also a symmetrical alkene. On the other hand, if you analyze propene, when the double bond will be broken, there would be 2 different radicals produced from each side. One side will produce CH2 radical and the other side has 2 carbon atoms and 4 hydrogen atoms, so C2H4. These are 2 different radicals. That means this alkene is an asymmetrical alkene. Let us take another example. This is 2-methyl-butene. Now again, if you break this double bond, both of the sides have different number of carbon and hydrogen atoms. The right side has 2 carbon atoms and 4 hydrogen atoms, whereas the left side has 3 carbon atoms and 6 hydrogen atoms. So this alkene too is asymmetrical. Now let us take a look at the Markovnikov's rule once more. It states that when an asymmetrical molecule is added to an asymmetrical alkene, the negative radical of the molecule, like in this case, we know that chlorine has a higher hydrogen, so chlorine would have a partial negative charge from the beginning. And when this bond is broken, chlorine will be the negative ion, there would be chloride ion. Similarly, when this bond is broken, we know that oxygen has a higher electronegativity than that of hydrogen, so oxygen would be the negative pole and hydrogen would be the positive pole, and when this bond would be broken, hydroxide ions would be produced, OH negative ions would be produced. So the negative radical from the molecule, like chloride in this case and hydroxide in this case, tends to bond with the carbon atom which is bonded to least hydrogen atoms. Now we know whenever addition is taking place, one of the radicals is going to form the bond with this carbon and the other one with this carbon. But this carbon has, that means, let's take a proper example of this type of reaction. For example, if we are reacting propene with HCl. Now propene is an asymmetrical alkene and HCl is an asymmetrical molecule which is going to be added to this alkene. Now as we know, for all the addition reactions, one bond of the double bond would be broken, leaving behind a single. This is what is left after the after one of the double bonds is broken. Okay, now we know that this bond is going to break and two different radicals would be produced. Chlorine already has a partial negative charge, hydrogen already has a partial positive charge, so the negative radical would form bond with the carbon atom with least number of hydrogen atoms. Like in this case, this one. This carbon is likely to form bond with this carbon, and hydrogen would obviously go to this. The compound thus formed will be 2-chloropropane. But this does not mean that in all the cases chlorine will form bond with the carbon atom with least hydrogen atoms. It may go to the other carbon atom. It will form in fact bond with the other carbon atom too. Because the rule states that the negative radical tends to form bond with the carbon atom with least hydrogens, but it does not say that it would form bonds with the carbon atom with least hydrogens always. It does not say that. So in some cases chlorine would be bonded to this carbon and hydrogen would go there. In this case 1-chloropropane would be formed. Now what happens here is that a combination of both the isomers is formed during the reaction. Let us balance the equation first. A combination of both the isomers is formed, but this one is in larger quantity as compared to this one, because the tendency of chlorine forming bond with this carbon is greater according to Markovnikov's rule, and this is the major product. 2-chloropropane would be the major product of this reaction, and 1-chloropropane would be the minor product of this reaction. So this is how Markovnikov's rule works. Now moving on to the mechanism of addition reactions. For example, let us take the example of this reaction, the addition of bromine to ethene. Now this is an addition reaction, and the type of mechanism is electrophilic addition. And this mechanism takes place in two steps. Let us see what are the steps of this mechanism. In step 1, a heterolytic fission starts to take place in this molecule which is to be added to the alkene, and that heterolytic fission is caused sometimes due to the polarity of the molecule itself, and in some cases polarity, like in non-polar molecules like this one, the polarity is introduced due to the presence of pi electrons. These pi electrons have a greater negative electric field which repels this electron pair away. That means even if this bond was non-polar in the beginning, it will become polar when the molecule passes close to the molecule of the alkene. So this will become partial negative and this will become partial positive, and this pair of electrons will move towards this bromine atom. So we have to show a curly arrow starting from the bond ending to this bromine atom which has partial negative charge already. This shows that this electron pair will be taken by this bromine during bond fission, while this bromine will not take any of these two electrons. Now, this positive radical, this partially positive radical so far will be attracted. This is now an electrophile. As I told you earlier, what are electrophiles? Electrophiles are electron-loving species. That could be either a positive ion or an atom with electrons. So now we have the curly arrow will start from this double bond and will end to this bromine atom with a partial positive charge. Now this is again because of the stronger electric field, stronger negative electric field of these pi electrons. Now what happens is that this electron pair will be shifted between this bromine and one of these carbon atoms. Suppose this one. Now this carbon atom is lacking one electron because one of its electrons which were shared in the pi electron segment, that has been transferred between this bromine and this carbon atom. So this carbon atom will now have a positive charge, and after this heterolytic fission, this bromine atom would take these two electrons and become a bromide ion, Br minus. Okay, now this species in which there is a positive charge on the carbon atom is called carbocation. This was step 1. Now in step 2, that carbocation will react with this bromide ion, and when you are showing anything as a nucleophile, you have to draw this pair of electrons with it, because you have to draw the arrow starting from this electron pair, and in this case there will be an attraction between this positive ion and this negative ion. So we can draw a curly arrow starting from this electron pair ending to this carbon atom. Again, I want to mention here that the starting point and the ending point of these curly arrows are very important. You must start this from this electron pair and must end it on the atom where it is moving, not to the positive charge, not to the positive sign. Now this means that this electron pair is being shared between this carbon atom and the bromine atom. And that will lead us to the product of this reaction, which is 1,2-dibromoethane. This is how you have to deal with the mechanism of these addition reactions of alkenes, and it doesn't matter which molecule is being added. Like I gave an example of Br2, it could be Cl2, it could be HCl, it could be H2, it could be H2O. In all cases, mechanism is the same. You just need to specify correctly that which atoms are going to have the partial positive charge and which atoms are going to have the partial negative charge. And you have to start and end the curly arrows very, very carefully. Their starting and ending points should be very, very clear in your answers. Sorry, my mistake, I have written this formula wrong. This was C2H4Br2. Please correct that. It was an addition reaction. Okay, the next reaction of alkenes in your syllabus is oxidation. And the oxidizing agent that we use for this reaction is acidified potassium manganate. We can represent it in the formula form like this. This H positive means an acidic medium and KMnO4 is potassium manganate. Okay, now you are all familiar with two very common oxidizing agents. One of them is acidified potassium manganate and the other one is acidified potassium dichromate. They are both pretty good oxidizing agents. But out of these two, potassium manganate is the stronger one. Potassium manganate is a little stronger oxidizing agent as compared to potassium dichromate. And alkenes would not be oxidized by potassium dichromate. They can only be oxidized by using potassium manganate. I want you all to note this down and I want you all to remember this because when the number of reactions that you have studied would increase, you will get to know that there would be some reactions which are common to both of these oxidizing agents. But this reaction is not. Oxidation of alkenes does not take place with potassium dichromate. I can see a question that if all addition reactions will be electrophilic addition. Yes, as far as we have studied so far, we have studied the addition reactions of alkenes. All of those reactions are electrophilic addition reactions. But that doesn't mean that all other homologous series who undergo addition reactions would undergo electrophilic addition. Like in aldehydes and ketones, they do undergo addition reactions, but their addition is not electrophilic addition, that is nucleophilic addition. You will study that in your segment of aldehydes and ketones. For now, the addition reactions of alkenes, yes, all of them, all the addition reactions of alkenes are electrophilic addition reactions. They have the electrophilic addition mechanism. Okay, now acidified potassium manganate is the oxidizing agent that is used to oxidize alkenes, and it can be used in two different ways. One in its cold and dilute form, and the other one is its warm and concentrated form. Now, if we use cold and dilute potassium manganate, that oxidation is called partial oxidation. And if we use hot and concentrated acidified potassium manganate, that oxidation is complete oxidation of alkenes. Let us take a look at both of these oxidations one by one. Now, when an alkene is oxidized partially by using cold and dilute KMnO4, it forms a diol. Like for example, if we are oxidizing this with acidified KMnO4, one way of writing this equation is to put oxygen in square brackets as reactants and write H positive oblique KMnO4 on the arrow. This shows that this oxidizing agent is providing atomic oxygen to this molecule. Now how this will work, one bond of these double bond would be broken and with each of the carbon atom an OH group would be added. A diol is formed. This is propane 1,2 diol. Potassium manganate. Now let us move on to complete oxidation of alkenes. Actually, I would like to use the full board for that, so I would give you a few seconds to copy this. Now moving on to the complete oxidation. And we can carry okay. Now in order to see this, I will give you a couple of examples. Like if I am talking about propene and in another case this is 2-methyl pent-2-ene. Okay, now let us consider the scenario. See, when we are oxidizing anything with hot and concentrated acidified potassium manganate, when an alkene is being oxidized by this reagent, now in this case both the bonds which were a part of the double bond would be broken. This time, unlike the partial oxidation, unlike the addition reactions, both the bonds in the double bond would be broken, always. Now you have to look at each of the sides after breaking these bonds, because we can have different scenarios. Like in this case, on one side, this carbon atom which was initially involved in the double bond, this is bonded to two other hydrogen atoms. This is one scenario. The other scenario is like this one. Like this carbon atom which was initially involved in the double bond, this carbon atom is bonded to hydrogen on one side and bonded to another carbon on the other side. A third possible scenario is like this one. Right here, this carbon atom which was initially involved in the double bond, it is bonded to two carbon atoms and no hydrogen atom is directly bonded to this carbon. So these three different scenarios lead to different sets of products. Like this scenario, when the carbon atom involved in the double bond is bonded to one carbon and one hydrogen, in that scenario a carboxylic acid is produced. And you don't have to change the formation of the side, you just need to show the functional group of carboxylic acid with this carbon atom which was originally involved in the double bond. So this carbon atom now has a functional group of carboxylic acid, and on the other side there was a methyl group that would remain unchanged. So this is one of the products. This is ethanoic acid because of presence of two carbon atoms in this chain. So this is ethanoic acid. Now let us take a look at the other side of the molecule. Now this side, this carbon atom that was initially involved in oxidation of this part of the molecule, and CO2 and H2O are formed because of the oxidation of this part of the molecule. Okay, I have a question about the mechanism, the electrophilic addition of alkenes. This question states that in electrophilic addition, why do shared pair of electrons move to the partial negative side of bromine molecule? That bromine, that is why it gained a partial negative charge, and that movement is because of the repulsion from pi electrons. As pi electrons have a stronger electric field, a stronger negative electric field, so they repel the shared pair of electrons away from one of the atoms. So the atom towards which that shared pair of electrons is moving, that gains a partial negative charge initially, and then the bond is broken and the atom becomes completely negative. That is because of the repulsion of pi electrons. Alright, now coming back to the complete oxidation by hot concentrated acidified potassium manganate of this molecule. This is 2-methyl pent-2-ene. Now again, this molecule has two different sides. When we break both the bonds of the double bond, we have two different sides. Now if you look at this side, the carbon atom involved in the double bond is bonded to hydrogen atom from one side, and to the other side it is bonded to another carbon atom. That scenario is similar to this one. So again a carboxylic acid would be formed. But in this case there are three carbon atoms in this chain, which would lead to the production of propanoic acid. I again want to mention it right here that do not change rest of the molecule's structure, just change the functional group. The carbon atom which was initially involved in the functional group would still be involved in the functional group, but the functional group would be different now. It was originally carbon to carbon double bond, but now it would be a carboxylic acid group. So now let us take a look at this side. In this case, there is a completely different scenario. This carbon atom which was initially involved in the functional group, that is the double bond, this is bonded to two carbon atoms. This is not bonded to any hydrogen atom directly, and in this case a ketone is produced. Whenever there is a scenario of this kind, a ketone is produced as the product of complete oxidation. So again, we don't have to change rest of the molecule, we just have to change the functional group. This functional group would be changed, and this carbon atom would now be bonded with oxygen. It would form a double bond with oxygen, and there was already one carbon atom at one side of this carbon and one carbon atom at the other side of this carbon, so that would remain the same. So the products of complete oxidation of 2-methyl pent-2-ene would be these two. This is propanoic acid, and this here is propanone. I'm repeating it again. when we are oxidizing alkenes by using hot and concentrated acidified potassium manganate, there are three different scenarios. First thing is that you have to break both the bonds which are the part of the double bond. After that, you have to look to each side separately, individually. See, there could be three different scenarios. One scenario is in which the carbon atom is bonded to two hydrogen atoms. In that case, oxidation products would be carbon dioxide and water. There is another scenario in which the carbon atom is bonded to hydrogen from one side and bonded to a carbon from the other side. In that scenario, a carboxylic acid is formed, like in this case too. The third scenario is when the carbon atom involved in the double bond is bonded to two carbon atoms from both the sides and it is not directly bonded to any hydrogen atom. In that case, a ketone is formed. And another reminder that do not change the rest of the part of the molecule, just change the functional group. This is the only scenario in which you have to change everything because inorganic products are being formed when a carbon atom is bonded to two hydrogen atoms directly. A question is that instead of carbon dioxide and water, can't an aldehyde be made? No, actually not. Whenever the carbon atom which is involved in double bond is bonded to two hydrogen atoms, the oxidation product is carbon dioxide and water, not an aldehyde. Now I will write this down for you in simple points so that you can copy that down and memorize what happens. Okay, so this is how the oxidation of alkenes work. I'll give you a couple of minutes to note this down. And this is as long as we will go in today's class. So if you have any questions about the reactions of alkenes, I mean the overall reactions of alkenes, you can start asking me. So guys and girls, I'm waiting for your questions. If you have any questions about this, you can start asking me. And the topics that are being covered, you should start practicing the topical past papers of these topics too at home. Because when I finish up the syllabus, I will start making videos about how to solve the past papers. And that segment would be very useful for you again. So keep on practicing. Are we supposed to balance? Asks you about the structural formula or the displayed formula or the skeletal formula of the organic products. Ask you the structural formula or skeletal formula or displayed formula or even molecular formula of the organic products formed. That would be asked in the examination questions. Okay, a student is asking me to give one more example. Okay, not a problem. But you give me the name of an alkene and I'll give the reaction of oxidation of that alkene. Are you going to give me an example or should I do it myself? Okay, doesn't matter. I'm gonna take another example like this compound here. Now this is a compound, this is 3-methyl-pent-2-ene. We can oxidize this by either way. We can use cold dilute KMnO4 and we can use hot concentrated KMnO4. If we are using cold dilute acidified potassium manganate, and the other situation would be when we are oxidizing it by using hot and concentrated acidified potassium manganate. See, now when we are using cold dilute acidified potassium manganate, this would be a partial oxidation and one of the bonds would be broken. The remaining molecule, let us write down the remaining molecule first. This is the part of the molecule which remains after one of these bonds is broken. Now these two carbon atoms have one vacant valencies. With each of these carbon atoms an OH group will be added. So a diol would be formed. Now this compound is 3-methyl pentane 2,3-diol. This is the product of partial oxidation of 2-methylpentoene. Now let us move on to the complete oxidation of 2-methylpentoene. In this case, both the bonds in the double bond would be broken, and the remaining, after breaking these bonds, the remaining sides, we have to check each side independently. First, let us check the left side of the molecule. On this side, the carbon atom which was initially involved in the double bond is bonded to one carbon atom from one side and to a hydrogen atom from the other side, and that scenario leads to the production of carboxylic acid. So in this case, there are total 2 carbon atoms, so ethanoic acid would be produced. Again, I am telling you not to change anything else from the molecule, just the functional group. So this is one of the products, ethanoic acid. Now let us take a look on the other side of the molecule. Let us ignore this one now. Now in this case, this carbon atom is bonded to another carbon atom from one side and to another carbon atom from the other side. That is the scenario in which ketones are formed. So again, we don't have to change other things. We just have to add the functional group of ketone to this carbon atom which was already a part of the functional group. So this carbon atom would be involved in a C double bond O, and the remaining sides would be unchanged, as to one of the sides a methyl group is bonded and to the other side an ethyl group is bonded, and this compound formed is butanone, a ketone with 4 carbon atoms. So these are the products of complete oxidation of 2-methylpentoene by using hot and concentrated acidified potassium manganate. I hope this was enough. Okay, there's a question that in addition reaction of halogens, why only Br2 and Cl2 are used, why not F2? Actually, it can be used. We just give the examples of Cl2 and Br2 because those are the more common reactions which are carried out in the laboratory or even in other industrial processes too. But yes, okay, and another question is that why Br2 should be aqueous? See, it does not have to be. For addition reaction of a halogen to an alkene, the halogen does not have to be aqueous. Bromine does not have to be aqueous. It would react even in its liquid form. But when it is aqueous bromine, it would undergo the same reaction, and that reaction is used as identification test for alkenes. As I told you during my previous video, this addition reaction of bromine with alkenes is used as an identification test for alkenes. So in order to use it as an identification test, we have to use aqueous bromine, because solution of bromine is brown in color, orange to brown in color, and when the product is formed, the product is colorless and water itself is also colorless. So aqueous bromine turns from brown to colorless. That is the identification test for alkenes. But we cannot carry out that as a test if we are using liquid bromine, because in that case there is no water which is colorless. So the bromine, if we are using a significant quantity of liquid bromine, that means only some of the particles will react with the alkene and the others would remain right there in the liquid. So the liquid would still be brown, it would not decolorize. So that cannot be used as an identification test, but yes, that reaction takes place. If we are using this reaction as an identification test for alkenes, then we have to use aqueous bromine, otherwise it is not a compulsion. I see some more questions coming on. Question states that does that mean bromine water is considered is aqueous bromine? Yes, it is. See, bromine water means aqueous bromine. Bromine dissolved in water, the aqueous solution of bromine, that is also called bromine water. It is not something different. It is the aqueous solution of bromine and it is used for the identification of alkenes. So guys and girls, if you have any more questions, you can ask me now. Otherwise, I'll leave the stream because I have scheduled another stream for A2 students. If any of you is preparing for A2 chemistry right now, you can join that stream too. I'll be live after 5 minutes when I turn off this stream. Okay, we see, I've seen a question and it is a good question actually, that when we oxidize these alkenes, why are the carbon atoms involved in double bond are the only ones that are oxidized? Why not the other ones present in side chains? See, there's a very simple answer to this question. See, the carbon atoms which are present in the side chains, they are just like alkanes. They are formed conditions by a strong or a weak oxidizing agents. They do undergo combustion, which is sort of oxidation, but they do not undergo oxidation by these common oxidizing agents. So they are very stable. Alkanes are very stable. Those bonds are not reacted very easily. So the atoms which are involved in carbon to carbon double bond, only those atoms are oxidized when we add an oxidizing or reducing agent, not the carbon atoms which are present in the side chains, because they are not involved in the functional group of alkenes. This is oxidation of alkenes. They are like alkanes, they are forming all the single bonds. So that part of the molecules is not supposed to be oxidized by these oxidizing agents. So I'm not seeing any more questions now. So I think that means that you have all understood this topic of reactions of alkenes. In my tomorrow's stream, we will start with the properties and reactions of halogenoalkanes. So keep on watching Infotainment Lounge. I hope this video was helpful. Thank you. Allah Hafiz.